Okay, so we are going to start this week talking about convergence of Fourier series. Okay, and so what we mean is the following. Our motivation is something like this. We have functions defined on the interval 0 to L. So far we've taken L to be 1 or pi, but let's just look at a generic L. And we want to know to what extent this following thing that I'm writing makes sense. The sum k equals 1 to infinity bk sine k pi over L x, and there's corresponding questions for cosine as well, but I'm using sine as an example because it's going to be very clear where there's a problem. Okay, so to what extent can we write f as a series like this? And even more fundamentally, we have to ask, what does this mean? What does equals mean? Okay, now we think we might know what equals means, but let me suggest that it's a little more subtle. And let me just illustrate this with the following example. So our most sort of basic understanding of what this means is that if I look at any x from 0 to L and I plug it in here, I'm going to get the same, and I plug it in here and I plug it in here, these two things are going to equal to each other. On the other hand, observe that if I plug in x is equal to 0 or x is equal to L on the right hand side, I'm going to get 0. Because if I plug in x equal to 0, it's sine of 0, which is 0. If I plug in x is equal to L, it's sine of k pi, which is also equal to 0. So the only way this can hold for all values of x from 0 to L is if f of 0 and f of L are both equal to 0. But there's a lot of functions, there's a lot of really nice functions defined on 0 to L that don't satisfy that. Okay, but if we think back to what's going on, do we really need this equality to hold for every value of x? And the answer really is no. What we need to hold is for all values of k, remember we were integrating, so we were doing something like the integral from 0 to L, f of y, sine of ly, little ly over big L, We were doing integrals like this. And so really the only thing that we need to be able to do is we need to be able to replace the function f here with this sine series here. Now, if this is true as a pointwise equality for every value of x, then we can definitely go from here to here. On the other hand, what if the only place where this pointwise equality fails is at the points 0 to L? In that case, this integral is still the same if we replace f of y with its series. Because all we would be doing in that case is just modifying this function at the point 0 and L. And that would mean we're modifying the overall integrand at two isolated points, 0 and L. And whenever you modify the integrand at 2 points, or a finite number of points like that, the integral doesn't change. So to do the things that we did in separation of variables, we don't actually need this to hold for all values of x. We only need something like this to hold. Okay, so what if we have two functions and we say something like f is equal to g. So we're going to kind of define a new notion of equality. F is equal to g if the integral from 0 to L of f of x p of x dx equals the integral from 0 to L g of x phi of x dx for all, we'll say for all smooth phi. Okay, well, let's assume that f and g are equal in the pointwise equality sense, but they just differ at one point. So maybe we have a graph. Let's say this is x, and we'll look at the graph of, this is the x-axis, this is the y-axis, I guess, whatever you want to call it. And let's say we have, let's say this is the graph of f. This is the graph of f. And let's say the graph of g is basically the exact same thing. I'm going to note that by doing dashed line, except for at this point right here, where g is equal to 0 here. Okay, well, observe that it doesn't matter what, it doesn't matter what phi is. If I look at the integral of this function from 0 to L of f of x, phi of x, so the blue one is g of x. This is going to equal the integral from 0 to L g of x, phi of x, and of course dx here and dx here. Okay, so this is really the sort of thing that we need, and this is what's going to happen. This is what we're going to get with the sine series here. And in the upcoming videos, we're going to look at two examples computing sine and cosine series for two different functions, and that's going to give us a pretty good idea of the extent to which we can write a function as its sine or cosine series, how we can do it, how, given a graph of a function, how we can find its sine and cosine series, and how it differs from the original function.